and most welcome.
Well, thank you very much for the kind introduction. Thank you very much for the invitation. Thanks for having me here. I've been visiting Uppsala quite a few times. It's always a pleasure to be here. Since the title of the symposium is Löwdin's Legacy, I decided not to talk about a very theoretical topic, but rather to talk about something which is more applied. In a sense, it's more chemistry. I'm a chemist, and so in the end, what things that we develop, we want to apply to chemistry, and so my talk will be about this. As you can see, actually my core interest is the exploration of chemical reaction networks, and networks shall just emphasize that I'm interested in chemical mechanisms, reaction mechanisms, but you will see they are so involved that they actually form vast networks, which typically you can't explore manually, and this is why we work on automated procedures. And so there is, at the end of the day, there is a lot of data involved, big data, and so whenever you think about big data, machine learning comes to your mind, and so we try to leverage machine learning to get the most out of the data that we have. And I should say, in this context, especially since Anatol is sitting here, I think it was Anatol who first told me about machine learning and tried to convince me to work on it, and unfortunately, and that must have been in 2010 or so, or maybe 2011, and unfortunately I wasn't listening. So I only understood what he tried to tell me, I don't know, 5, 6 years later, maybe 7. But eventually I understood. So to me, machine learning is a big glue to tie together all of the different kinds of data that we are producing. And that's why it's so important for exploring reaction mechanisms. Let me tell you a bit about what to expect from the lecture. So I already anticipated that this is about big data. So we need massive computational campaigns to figure out what kind of reactions are possible for some reactive system, right? And that will also involve the interplay of concept and algorithm development to make that feasible, software engineering, of course, and in the end, I'd like to be predictive. I think this is, should be much more emphasized in our community. There is error assessment, or how it's called in computational science, uncertainty quantification is a major issue, of course, for any computational work, but that work in computational chemistry that rests on quantum chemistry is kind of lacking this. Probably the reason is that we believe that in the end we know the final answer, we just can't get there, right? The problem is we need more than a gut feeling how good the data actually is. And in order to do this error assessment, we will need some sort of benchmarking. I will comment on this later on. And we need to do that automated in a rolling fashion. Unfortunately, for time reasons, I can't cover that here. And what we also need is, since we want to develop tools that allow us to look at any sort of chemistry, we need to be able to look at reactive chemistry in complex environments, not only solutions, not only enzymes, but could also be some nanoscale structure in which the reactive system is embedded. But when you think about that, we have no tools in our hands to in an efficient way, set up atomistic structures to do that, right? And so we are working on this too, but also here for time reasons, I can't go into that. So this is how I see chemical reaction networks. Basically, the network or the mechanism is kind of our mechanistic understanding of a chemical process, right? And as you will see, we need to explore very many reactions here in order to figure out what a reactive system is actually capable of. We need to do that with computers, and we need to store it in computers, and the huge data needs to talk to our mind somehow, and in the end we need to connect to experiment to verify that what we see is really what is there. Let me introduce a bit of notation. So this is a sketch of a network. So we have reactions and we have compounds. In chemistry, this is how we think about chemical transformations, right? You start from some sort of compounds here, indicated by the green dots. There will be a reaction forming new compounds indicated by this dot. But in fact, it's much more complicated. Each of these compounds has different representations. Typically, we call them conformations or conformers, right? Because they are different forms of the same type of connectivity of a molecule, and all of these can be reactive, and they typically don't have the same reactivity. So we need to take all of them into account. right? And then the same holds then true for the reactions. Each of these reactions, so if you like this, what's in the middle is kind of the mechanism, and then we have the resolution of the mechanism in terms of elementary reaction steps, where each compound is dissected into a set of conformations or conformers, and all the conformers react to other conformers belonging to new compounds, and giving rise to various elementary steps that eventually are important for a single reaction step. And in order to figure out what is going on, you really need to look at all of this, because you can't afford missing any important step, right? And there's no other way than really inspecting all of them. But that is difficult. It's probably not that difficult if you have already a good guess to what kind of system a reactive system will react, right? But say if you don't know this, or if you are totally unaware of reactions a system can undergo, like take its catalyst and you don't know anything about the decomposition reactions, which basically means that you have no clue about turnover number, for instance, right? Then you need to have algorithms which are able to explore the chemistry that you are not aware of. And that can be done. And this is an example. It's an example shown to highlight that the vastness of the data that is being produced. This is a reaction of propylene with dioxygen, still without a catalyst, just to show you what happens. Typically, you suffer from a combinatorial explosion. What can go on? Of course, it depends on reaction conditions, right? But in general, even under mild conditions in condensed phase and so on, the number of reactions to be considered is huge. This is a brute force exploration where we basically try everything possible. We use approximate DFT for the pre-screening because otherwise it's too costly. Approximate DFT means tight binding DFT. There are various groups in the world who are trying to develop reliable tight binding DFT methods, which are far faster than standard DFT methods, at the cost that the accuracy breaks down. The problem here is not that much that the energy is not that accurate, because that can be corrected afterwards. The problem is that often the structures suffer too. So this is an issue that is still being investigated. Propylene and oxygen are our two reactants from which we start, and the settings are a bit conservative so that we can deal with the data somehow. So for instance, we don't consider conformations here, although we can. We have algorithms that can do that. Probably you know the RDKit program, which is heavily used for organic chemistry. We have developed something similar that's called mole assembler that works for the full periodic table, and that can explicitly generate conformers. Of course, if the system is too big, you need some sort of sampling. You would resort to dynamical approaches. We restricted the barrier heights to be less than 200 kilojoules per mole, and the size of the compound that is generated in the reaction to this formula. The resulting network comprised 4,200 compounds. These are compounds, not the structures, not the conformers, right? And they are connected by 6,300 reactions. These are the reactions, not the elementary steps, more elementary steps. The computational cost was 1 billion individual energy calculations for the exploration to figure out what the system is really doing. And it took 5,000 days of CPU time. This is kind of a sketch of all the structures and color-coded kind of the exploration progress. Of course, you can't see anything in there. It's just the idea is to tell you that no matter how simple the system is, in terms of elementary steps connected to a reaction network, this is very complicated. And of course, you don't want to do this brute force. You want to save computer time, especially if the reactants are getting larger, right? How do we do that? Many groups in the world use graph-based approaches. We try to develop schemes that are agnostic in the sense that if I encounter an element from the periodic table, I still want everything to work. For instance, if I suddenly look at organic chemistry that is catalyzed by transition metal atoms, it should still work. So we have invented something that we called first principles heuristics, where we try to exploit information from the electronic wave function that is available for each of the reactants, of course, in order to figure out whether, say, a pair of possibly active atoms that could react is actually reactive or not. And here the point is that we have kind of a weak condition on it. We don't ask for, let's tell the electronic wave function of the stable minimum structures where these molecules will react. It will already be sufficient to know what parts of the molecules are unreactive, because then we don't need to test them, right? And we do this by concepts that have been developed in the context of conceptual DFT, but they are, of course, they hold true for conceptual electronic structure theory in general. This is what I'm talking about for those of you who are not that familiar with this. In conceptual DFT, and you can extend that, as I said, to conceptual electronic structure theory in general, you basically look at the Taylor series expansion of your electronic energy, which governs everything, because the potential energy surface on which the reaction runs is, of course, the Born-Oppenheimer electronic energy surface. Well, you Taylor expand that electronic energy in terms of the parameters that can change. For instance, electron number, external potential, right? And this is an example. The electron negativity is defined. That has already been done in 1961 by Ichkovsky and Margrave, but also at the same time by Hinze and Jeffy. Can be defined as the derivative of the electronic energy with respect to the number of electrons, which is conceptually clear. If you think about the number of electrons needs to change in order to figure out whether an atom or part of a molecule is more or less electronegative at constant external potential. Right? And then there's this paper from 1978 by Parr that basically said the same and was the basis for the development of conceptual DFT. And in this Taylor series expansion, all the derivatives are interpreted as concepts, and the concepts tell you something about the reactivity of the system. The problem is, though, that the concept evaluation takes place at the minimum structures. Right? So you try to figure out what the barrier height is, what the kinetics is of a system by looking at the stable minimum structures. And that is, of course, an issue here, right? And in fact, it's not clear right now how predictive conceptual DFT actually is. Despite of decades of work, people have mostly used it in a descriptive way. So you know the result, then you understand what's going on in terms of the notions that are introduced in conceptual DFT. So it will be good to figure out how predictive this is, right? I mean, we have seen that it can be used, but that has not been done in a rigorous way. And so what we are currently doing is we use our machinery to produce vast amounts of data on chemical reactivity, also including reactions that are not feasible under external conditions, temperature, pressure, and so on, right? To figure out whether the chemical concepts have a chance to predict what's actually going on. And we use our machinery for this. Let me tell you a bit more about this machinery. It's called Chemoton, and you see we have now version 2.0. The first version of Chemoton was published in 2017, the latest one 2022 this year. It's an open source software that is freely available from our web pages. Everything we do is available from our web pages. At times it takes a few months until it's available, because after the publication of the paper, because making the software usable for everybody is a huge effort, and that simply takes time. So what do? We look at intermolecular and also intramolecular reactions. We can do association and dissociation reactions, and we can have bond modifications, events that go beyond one bond modification. Then what we do is we figure out what are the reactive moieties, for instance, indicated here in blue, this atom here, the bond there, and we orient them, so we make them react, and of course something else can happen to the rest of the molecules, and so we screen also for various orientations. And then we have algorithms that make the reaction occur. Right? I will comment on this on one of the next slides. Of course, you would like to know how good this actually works, and so we have assessed the capabilities of the software by looking at 184 diverse reference reactions, really a diverse set, designed such that our methodology is really challenged. You see here, this is kind of an overview of the reactants. You see this is a reactant index. These are the 69 reactants that are considered, and that is their size in terms of the number of atoms. More than half of it are unimolecular reactions, then a huge fraction biomolecular reactions, and then there's also a thermomolecular reaction. Here's an overview of the reactions that we consider. As you can see, it's really a really diverse set. Now, what results do we get? Well, first of all, for the screening here, we used again tight binding. Right? And there is this tight binding method that was developed by Stefan Grimme's group, and then there's also this older DFTB3 type binding, which we implemented in our own semi-empirical code. Here we use Stefan Grimme's code. So we have these two different tight binding approaches, and then we have two different algorithms, which we call Newton trajectories, 1 and 2. That is based on work by Quapp and Bofill, who criticized the work of Maeda on the AFIR method, and so we took all the experience that was available to come up with these two algorithms, NT1 and NT2, which I described in that paper that was published this year. Here you see from the reactions that we should find, we don't find everything, right? We find here 65%, 80%, 74%. It's important to note that whether we find everything that we should find depends on the electronic structure method. So in part, you see here the deficiency of the fast electronic structure method, and we expect this to be improved in the future. And then, moreover, the rest that we would not find, we can't find because we are not searching for this. For instance, there are reactions that involve bifurcations, and those cannot yet be found with our software. So this is all fine because we understand why we don't find 100%, but the key point here is we find more than we should find, right? So we also discover reactions that were not described in the literature for the systems that we studied, which is interesting because in the end, the tool that we are developing is kind of an explorative tool that should generate ideas, things you might have forgotten or not thought about in terms of chemical reactivity. There is another overview here which tells you about it's a classification of systems like bimolecular, unimolecular, transition metals involved. And these are the critical cases that we should not be able to treat, and you see this is what we find, this is what we miss. And again, the failures are due to the approximate electronic structure model and to the fact that we miss some reaction types. Okay, so we can do this, right? So we can look at reactive systems. And then we need to know, of course, how good the data is. You already saw that the tight binding approach, of course, can only be the starting point. In the end, the refinement must go to DFT and beyond, to electron correlation methods. Electron correlation methods are easy to switch on because everything here needs to be driven in a fully automated way if you do coupled cluster. But of course, you know that coupled cluster can have an issue when you leave the single reference regime, right? When Hartree-Fock does no longer work well for your system, then coupled cluster won't do a good job either, and you need to go to multi-configurational chemistry. We can even do that in an automated way. We use therefore CAS-SCF type methodology, for instance, implemented in the Open Mulcast program. And the CAS-SCFs that we will drive usually will be of DMRG type, and there's this QC Markus program that we contributed to the Open Mulcast package, which can be driven in an automated way. Automated means that we can automatically also select the orbital spaces for these reactions. Okay, so we have also correlated data. Still, we don't know how accurate, how predictive our network really is. And because we can't have that data for all of the nodes. And so we need, in the end, uncertainty quantification. Since we will have the expensive correlated data only for a few nodes, we need to find a way to figure out how accurate or inaccurate the DFT results are for the rest of the nodes for which we don't have any reference data. And here we follow a Bayesian approach, which basically means that we try to transfer the knowledge from where we do have the reference data to those regions where we don't have the reference data. And for this, we exploit machine learning. So the idea is to set up a statistical model, a machine learning model, that tells us about where to expect high or low accuracy from the more approximate electronic structure methods, such as DFT, compared to coupled cluster or strong correlation approaches, in order to understand where we will need more reference data. If you want to read more about how we do that and why we do that, I'd like to invite you to look at this paper in the Israel Journal of Chemistry. And I'd like to in the second part of my talk, I'd like to elaborate a bit on this idea. In order to do that, of course, you see, you have, for certain structures, you do have accurate results. For other structures, you need to rely on DFT, but you don't know how good it is. In order to compare this, right, you need some measure that allows you to compare different structures in chemical space, right? And the machine learning community has come up with a huge set of such measures. And I picked two for our analysis here, the Coulomb matrix and the smooth overlap of atomic positions. Anatol in the audience is well familiar, of course, with the Coulomb matrix, and the smooth overlap of atomic positions was developed by Gabor Czarny and co-workers in Cambridge. In short, it's called SOAP. Right? I picked these two not only because they are widely used, but also, as you will see, they can be related to electronic structure theory. In the analysis that we did for these descriptors, which are the key measure of similarity and hence transferability of knowledge in chemical space, we will also introduce two new descriptors, which we call Coulomb list, you will see, and the smooth overlap of electron densities. So this is basically the situation, right? We have these physical descriptors of molecular similarity. They need to encode the physics of the molecules somehow. We have a lot of data generated, and we use the machine learning to get information about prediction and uncertainty. We exploit a data machine learning approach, which was, I think it was pioneered also by Anatol, where the idea is that you learn differences rather than absolute values, and the hope is that you get away with less data. Our method of choice so far has been Gaussian process regression. You can also choose a different type of machine learning model. But so far, we have been pretty happy with Gaussian process regression. Basically, the idea is that you have a few reference points indicated here as the black crosses. And you're looking for an interpolation, and of course, because you need information in regions where you don't have a reference point, and these statistical models comes with information about variance that can be interpreted as uncertainty. And of course, if the data density is high, like here, then the uncertainty is low. In regions where you lack data, uncertainty will be high. And we just need this as an indicator to tell us where in the space to which we are going with the automated reaction mechanism exploration do we need reference data. Right? And so this is how we exploit the statistical model. There is a Gaussian kernel that measures similarity, and that has, you see this exponential function here, there is a hyperparameter L, and the key thing here are the two input variables. If the two inputs are the same, then the kernel yields 1. And these inputs are the measure for similarity. Let me give you an example how that can be exploited from our work. Of course, many other groups have done that in different contexts. For instance, we looked at this notorious semi-classical way of assessing dispersion energies in DFT, where you simply use Lennard-Jones type attractive expressions to capture the dispersion attraction in DFT, which typically completely neglects any sort of dispersion, right? And so the question here is, can we improve on this? And the way we set up the inputs for the Gaussian process regression was to consider the pairwise energy contribution from the semi-classical energy expression as a matrix. Pretty much as the Coulomb matrix, which will be introduced on one of the later slides. And in the case of the Coulomb matrix, what you would do is you would diagonalize the Coulomb matrix and use the eigenvalues as the input for the kernel. And here we do the same. We consider this to be a matrix, we diagonalize this and use the eigenvalues as a kernel. And then with this statistical model, you can actually improve on the semi-classical dispersion corrections and make them even more accurate. Since that is not the topic of my talk, I'd like to go back to the reaction networks. But first of all, let me give you a brief glimpse of some of the work that we have done on delta machine learning and uncertainty quantification. We have used it also in the context of self-parametrizing atomistic force fields and in the context of QMMM. This relates to the part of where I don't have time to tell you about, where we construct nanoscale models in an automated fashion so that atomistic structures that are larger than small molecules are easily accessible to us. I will focus on this part though, chemical reaction networks and uncertainty quantification, but I would want to mention too that we have kind of a history looking into uncertainty quantification for computational chemistry. In previous years we have used techniques like bootstrapping and jackknifing to assess the accuracy of physical chemistry models. that are evaluated with quantum chemistry schemes. Okay, so let's go back to this error-controlled exploration of reaction networks. So you already know that we look into these massive reaction networks with first principles methods. Now, the observables that we basically, the most important observables that we look at is, of course, the energy, and of course, first and foremost, the electronic energy. Then we take the statistic model that we evaluate, that is a Gaussian process, and we obtain the error estimate from there. Now, if the error is above a given threshold, this idea I have already explained, then we launch a correlation reference calculation in order to get a more accurate electronic energy, and that information we try to then transport through the method, through the network. Here is a sketch that explains the idea, say, if in the network we have one molecular structure, for which we do have the reference data, then we take the descriptor for molecular similarity, and in this work we chose SOAP, will be introduced on one of my later slides. You haven't seen the definition yet, which tells us how similar the other structures are compared to the structure for which I do have the reference data. And we applied this to a network of structures. I think that was also produced in Anatole's group, because it's available and widely used in the machine learning community, to a network of structures which are all on the same Born-Oppenheimer surface. And we started the exploration from some point, and the exploration progress is color-coded here, and then explored the surface. With the Gaussian process, we assessed having some information from coupled cluster theory, which is indicated here by the red point. So each red point represents a structure for which we do have coupled cluster information available. Now we expand from here with the Gaussian process, and the Gaussian process tells us as soon as we reach regions where the difference in molecular structure has grown so much that it's better to have a new reference calculation. And you see that that automatically we defined in a very efficient way for which structures we actually need reference data in order to figure out what the accuracy in terms of the statistical model, what the accuracy is of all the other structures in the network. Okay, now the question of course is how reliable is this? Because for some reason it will depend, for an obvious reason it will depend on the molecular similarity measure, right? So let's look into these measures. The idea is that we want to root the descriptor in order to understand it. So this is not a machine learning or big data perspective, this is a quantum chemistry perspective, into electronic structure theory, because we believe that it is then reliable, transferable, and interpretable. As I said already, we pick these two popular descriptors, the Coulomb matrix and the smooth overlap of atomic positions, because as you will see, we can link them to electronic structure theory through the first Hohenberg-Kohn theorem. And in this course, we introduced two new descriptors, Coulomb lists and the smooth overlap of electron densities. Here you see, finally, you see the Coulomb matrix. The Coulomb matrix is computed from the nucleus-nucleus repulsion term in the electronic energy. So each of these terms, which taken as a whole, as seen here, are a part of the electronic energy. Each of them now forms an entry in the Coulomb matrix. And of course, there is no contribution from this to the diagonal. And in the machine learning community, they have come up with more information that is encoded in the diagonal. And probably Anatole can tell you more about why this is done, but I think we don't need it for our purpose here. So you see the entries of the Coulomb matrix in the electronic energy expression here. What I also plot here is the external potential, and the external potential can also be written as a list, and the nucleus-nucleus repulsion as well, in such a way that that we have one of the double sums here running over the individual atoms in the molecule separated. So for each of the atoms, we have one of these entries here, and we will have one of these entries there. And of course, there's more to the energy, like the electron-electron interaction and so on, which I just put into this term because I don't want to talk about that. Okay, now I'd like you to consider the following dilemma. This is in the context of reaction networks, right? Say you have reactants, you do have products, and these are in an elementary step connected through a transition state. Structure-wise, obviously, the transition state is close to the reactants, it's close to the products, and the transition state structure is closer to the reactants and products than the reactants and products are close to one another, right? So the transition state is more similar to reactant and to product then are reactants and products. And of course, we want to measure molecular similarity. Now, in terms of electronic structure theory, you know that stable intermediates like reactants and products are often easy to describe, right? And transition states are hard, electronic states are coming down, electron correlation is more of a problem, and DFT will have larger error bars there. So we know that although the transition state structure is more similar to the reactants and products, it will probably suffer from a larger error. And the question is, can we unfold this by use of a proper descriptor? In order to study this, we take a reaction. This is from the same set that I was talking about, but now we actually let this molecule be transformed into that molecule of the set, and we have a transition state here. Now, keep in mind that the entries in the Coulomb matrix or the nuclear-nuclear repulsion itself has nothing to do with electronic structure theory, and it is not related to the external potential, which is the interaction of the electrons and the nuclei, right? But still, it correlates. And so this is our connection. So here, you see on the x-axis the atoms in the direction that you have seen before. The carbons are here, the hydrogen atoms there, carbon atoms here, hydrogen atoms there. This here on the right-hand side, that is for the information for the external potential list, so the external potential resolved atom-wise, and here it's the Coulomb list, right? And what you can see is already by visual inspection, you basically get the same information. So what I'm saying is that the nucleus-nucleus repulsion encodes the same information as the external potential, right? And so you, rather than evaluating the external potential as a descriptor, which would be more expensive because you need to evaluate an integral, it's much easier to go for the Coulomb matrix or the Coulomb list. Now let's look into the smooth overlap of atomic positions. Just a second, I forgot to mention. Also, the Coulomb list by design, let me go back to the equation. By design, since we have this resolution that we get this term for each atom J, can be used as a complete substitute for the Coulomb matrix. The Coulomb matrix typically involves the diagonalization, where you lose information and you take the eigenvalues in the machine learning process. Here you have the same type and same magnitude of information, but you have still physical interpretability because you have this assignment to atoms, which we consider to be useful. Now, back to SOAP. SOAP was designed as a scaffold density. So we are still talking about molecular structure similarity. And the idea is, rather than to have explicit positions, Cartesian coordinates, to broaden these positions in order to make it a more versatile tool for comparison of molecules in chemical space in general. Right? And the way it's done is, there will be an S-type Gaussian function which is centered on each of the nuclei here, depicted here. And of course, in principle, you can have different exponents here if you wish. So this way, you broaden the information of where the nucleus sits, right? But still, in the end, this is a density distribution that describes the distribution of the nuclei, in a sense. But of course, when you look at this, it also relates somehow to how we compute electron densities, right? And I'm coming back to this in a minute. Now, how do we work with the scaffold density? Well, say you have one scaffold density for one molecule, like this one, and you have an O, you want to compare it with the scaffold density of another molecule, you need to figure out what is the best fit, right? And the way it's done in Gabociani's work is a rotation operator operates on one of the scaffold densities in order to rotate it with respect to the other scaffold density and then calculate an overlap. And of course, then the kernel needs to consider all the rotations, right? So, because you can't tell which of the rotations is actually the best rotation. To go for one best rotation is not very efficient. Instead, it's better to evaluate this integral where you look at all rotations. This way, you get the best picture of how similar two scaffold densities are. Okay, let's go back to the electron densities. The way we, as I said, the way we evaluate the electron density is very similar, in fact. Apart from the obvious that we have a more complex representation of the density in terms of many Gaussian functions. First of all, our Gaussian functions in a molecular calculation in this linear combination of atomic orbitals will be always a product of Gaussians, right? And there is more than one per atom, of course. But of course, you know that these two Gaussians, through the Gaussian product theorem, form a new Gaussian, right? So that's not the problem. In fact, you can write this electronic density in this form. The problem for the formalism actually is that these Gaussians contain high orbital angular momentum quantum number Gaussians, and they are hard to evaluate in the analytical representation here, because these integrals are solved analytically, or can be solved analytically, and they are easy for S functions. They are super hard for higher L Gaussian functions. But that can be solved too. And of course, it can be solved, right? But it takes too much time. And if you have a big data problem and the evaluation of the descriptor takes too much time, then it's useless. So in the end, you need to go, and SOAP is already not very cheap. So you need to go back to S-type functions in order to be feasible. And we picked simply lobe functions, which is this old trick from the 70s for easy integral evaluation, where, for instance, a P function is modeled by two off-center S functions with plus and negative sign, right? So this is what we do. And then we can go through the same. So we take the electron density actually from a decent electronic structure calculation, for instance, from Hartree-Fock will be sufficient, right? And then we go through this procedure, map everything to lobe functions, and we have a representation of the electron density that can be used through the SOAP machinery for comparison of molecules. And here you see the result for our two structures and the transition state. It's the same reaction here. On top, you see the results that we get with SOAP, and here we get these results we got with the smooth overlap of the electron densities. And basically, what you can see is the picture is the same. So we get the same information, and also the smooth overlap of electron densities allows us to discriminate a bit more compared to the standard parameters in SOAP, but of course you can tweak the parameters in SOAP to better model the lowercase here, and then it will be more efficient. What do I mean by tweak? Well, there are these exponents, of course, in the Gaussians for the SOAP that can be tweaked in order to get a better match here. The key point here is that through this comparison, we basically can link the smooth overlap of atomic position, which was a structural descriptor, to the electron density, which gives us a direct link to electronic structure theory. This brings me to my conclusions. I have told you today about how we explore vast reaction networks in a fully automated manner. So we have automated procedures that are driven by automated meter programs in a fully autonomous way. We do have uncertainty quantification and need uncertainty quantification in order to understand how good the data is, or what kind of chemical conclusions can reliably be drawn from the data. And we do this with rolling benchmarking. Right? So far, we have looked into Gaussian process regression with delta machine learning as a way to assess these uncertainties. Other options are, of course, possible. I have told you about two new similarity descriptors that we developed through our efforts to better understand molecular similarity descriptors, Coulomb list and the smooth overlap of electron densities. Both of them relate directly to the first Holmberg-Kohn theorem, which I think is nice. And the Coulomb list allows for a direct interpretation, which would be a bit more difficult for the Coulomb matrix after this mysterious diagonalization step. And we can now understand or use SOAP as a model for the smooth overlap of the electron density, if you want to. Well, all this work that I presented to you was done by the great people in my work. You see a current group picture here. These are the names. The second part of the talk was mostly based on work by Stefan Gugler, and all of the others are involved in the development of this Chemoton machinery. Financial support was from ETH Zurich and the usual suspects. And that's all I wanted to tell you. Thank you very much for your kind attention.
Thank you very much, Markus. Very interesting talk. So now we open for the questions.
Thank you very much. That was awesome. I enjoyed it very much. I'm allowed one remark on.
Of course.
on the mysterious diagonalization of the Coulomb matrix. So initially, when I proposed this, right, the idea was to work with the matrix, not with the eigenvalues. But then you had this sorting problem, which is tricky as you compare the different minima, right? And so an easy way out are the eigenvalues then, which are invariant with respect to indexing. That was the primary reason why we diagonalized it, but in subsequent work, actually on that PRL, there was a comment where they showed as you move the atoms out of the minimum, there are certain modes along which the eigenvalues of that matrix are invariant. And so you could not use it as a potential energy surface map anymore, right? We've always seen that the eigenvalues were unique for minima structures, but not when you displace. Anyhow, so after that, we mostly went back to sorted Coulomb matrices without the diagonalization. Right?
Yeah, I mean, I'm fully aware of the reason why you did that. And for the Coulomb list, we have the same problem, of course. We also need the sorting.
Exactly. Yeah.
And it turned out that sorting then just by magnitude is sufficient for the purpose, which kind of surprised us. But the key point still is also here that you don't lose this connection to the individual atoms. Just because
absolutely, yeah. And I greatly appreciate that, right? So it's wonderful to see this work for reactions too. And my second question is more of a question. You stated that the transition state geometry is closer to reactant and product than reactant and products to each other, right? Is that necessary?
In terms of configuration space.
Yes.
So when you take phase space, it's obvious that this on your way to the product, you will pass through the transition state structure.
Right, but is it necessarily true? I mean, I could imagine a transition state geometry far away from a product and reactant.
Oh, so you're thinking about a path which goes like this?
Yes. Is that?
Well, I wouldn't exclude that.
Okay. All right. Thank you.
First of all, thank you very much. Just to follow up on Anatoly's last question here, aren't transition states much more open shell electronic structures, and in that sense, different from the reactant and products?
That's a dilemma. So structure-wise, so if the path through the configuration space is like this, and you go from reactants to products here, and the transition state is somewhere on the way, then you have this structural similarity, but electronically, of course, they are totally different. And that's the dilemma.
All right, but that's...
And so I'm of course, I'm not a big data person. I'm looking at the field with admiration. And a big data person probably would tell you, with sufficient amount of data, it doesn't matter. But I would argue, since probably you don't have that amount of data and you would like to fold in electronic structure information to account for it.
My question that I wanted to ask before I heard this was, so you selected a Gaussian process regression for the delta machine learning. And I would use a method like that over a neural network if I had accurate data and I knew there was actually an exact function behind this. Whereas I would use a neural network when I had didn't know really what was going on and I had noisy information. So could you dwell a bit why you selected the Gaussian process regression? I mean, you also have, with the Gaussian process regression, you have this covariance matrix you have to invert, whereas with the neural network, you have to train it.
Absolutely true. So the Gaussian process was our first choice. One reason to go for this is we should think about a reaction that goes over the surface, right? And the surface is mapped out with some cheap electronic structure model. It has some error. But typically, the error is not homogeneous, of course, so it will be different for different structures, but the change will be smooth, right? And so with this assumption in mind, we went for the Gaussian process rather than for the neural network representation. But it's just like, it's our first try, so this is not the end of the story yet.
I have a follow-up question. You show there is a good correlation between the Coulomb list versus the external potential list. And then if we follow this dilemma between structure and electronic structure, would you think this correlation still holds for the transition states?
Yeah, that was our hope, but it has not come true so far.
Okay.
This is what I can say.
All right. Is it closer? Yeah.
I don't think so.
Thank you very much. I was wondering if you could elaborate a bit on how you identify the reactive moieties in this Chemoton approach.
Yeah. So what the data that you have seen was first of all brute force. So that is one option in the program. And in the brute force approach, basically all atoms are considered reactive and are pushed upon one another while considering orientational degrees of freedom in the rest of the molecule. That's the brute force approach. The first principle heuristics tries to prune this by figuring out which, of course, that would be perfect, which are actually the reactive atoms. But like I said, it would already be sufficient to figure out what are the atoms that can be considered under reaction conditions as unreactive, like CH bonds, if the energy is low or whatsoever, right? This is an example. And then the other way to speed up the brute force exploration is, of course, having these tight binding approaches, if they work. Currently, my opinion is probably neural network potentials have a better chance than tight binding, but we will see in the future. But that's kind of a pre-screening approach where there must be a refinement step afterwards.
I have a question too regarding this. What's the main difference between the AFIR from Japan? You said it's the algorithm is different, wherein you have. I'm more familiar with AFIR, so if you could elaborate with the difference between the Chemoton and the AFIR.
If I may, I don't, but I'd like to point you to that paper by Quapp and Bofill.
Okay.
So so that was, I think, in theoretical chemistry account. If you find it quoted in this reference, of course, right? So I invite you to go and read about that there, because it's their criticism.
Thank you.
Do we have other questions? If not, then we thank the speaker again. And
thank you very much.